by popular demand from at least one person. So, point vortices. So originally, this goes back to Helmholtz in the middle of the 19th century, and Kirchhoff, who looked at it in the plane. So you can do this on any surface, Riemannian surface. So I'm not going to introduce all the fluid dynamics behind it. So it's a delta function of vorticity. So the vorticity is concentrated at a point. It's a singular point because it's a delta function. So a point vortex comes with a strength, which I shall call gamma. And so vorticity is about rotation of the fluid. Is it 2 pi gamma? Is that right? 2 pi gamma, not gamma, yes. In the positive direction. So if gamma is negative, so fluid it flows in circles with speed one over the distance. So very close, it's going extremely fast, and far away, the speed tends to 0. 1 over r. So because this one is, the fluid is rotating, it makes these move. They're carried by the fluid. It's a fundamental principle of fluid dynamics, is that the circulation is carried with the fluid. So the circulation is carried along by this fluid flow that caused by this one. So this causes this one these two to move. This one is rotating this way, so it causes this one to move up here. These ones, you have a linear superposition of the velocities caused by the individual vortices, and the strength tells you proportion gamma over r. So the bigger gamma is, the faster the fluid motion is. Oh. So the dynamical system is Hamiltonian. So I think this is historically interesting because, as far as I know, it's the first time anybody discovered a Hamiltonian system that was not kinetic energy and potential energy. So before then, Lagrange, of course, didn't talk about Hamiltonians, but Lagrangian systems, Hamilton and Dirichlet and Riemann and all these people, well, at the same time. But all the study of Hamiltonian systems was kinetic potential systems, mechanical systems, whereas this is the first one which is definitely not of that form. There's no kinetic energy involved. These do not have any inertia. There's no mass. And the dynamics is a first-order differential equation on the space of configurations. It's not second-order differential equation. But it's still, as I think Kirchhoff discovered, it's still Hamiltonian. So given capital N, so I'm going to, this is in the plane R2, but it's convenient to use complex numbers. So I'm assuming that no two of the points collide. In fact, in general, the vector field is not complete on this space because collisions can occur in finite time. So that's not right. Yes, that's not complex conjugate. It's complex conjugate if you write it in the numerator. And there's an I in there, 1 over 2 pi I. So that's a nice closed set of differential equations, not too complicated. So this is Hamiltonian in the sense, define H to be, get my coefficients right, minus 1 over 4 pi. So sum going from 1 to n, but j not equal to k. And then the equations of motion in this form and that can be made into a Hamiltonian equations. This is written in complex notation, but there's the complex conjugate one as well. So you have 2n of these equations, and altogether. Now I can't remember because I didn't prepare this question. Something like I can't remember the sum. Some Q and P choice that's quite simple, but if you put those in, it gives you the right equation. So you can make this look just like the usual Hamiltonian. I'm sorry, I don't remember what the expression is. I don't think I have it written down here. No. So this system has 3 conserved quantities that are known classically. They can also be derived using symplectic geometry because they correspond to symmetry group SE2, Euclidean group, translations and rotations in the plane, which has dimension 3. And by Noether's theorem, there are 3 conserved quantities. I'm going to write them as J. So that's in C, so there's 2 conserved quantities there. So that's like a center of mass. I think to get it quite right, one puts an I in front. And this one has a -1/2 as a factor. So total of 3 conserved quantities. So this is, as the points move, these 3, under the dynamics, the real imaginary parts of that, and this quantity is conserved. Are there any equilibria? The answer is there may be. So actually there are, in general, there are lots of them. So let me just look at a couple of examples with low number of point vortices. So if there are 2 vortices, well, it's pretty clear this one makes this one move. So there are no equilibria. And this one makes this one move. And for 3 vortices, we have equilibria only if where's it gone? it's not there. Sorry, I'm looking in the wrong place. No, it's not there either. Okay. I believe it's gamma 1, gamma 2. Equals 0. That's symmetric. So, for example, if all three are positive, then there cannot be any equilibria. And that's not surprising because however you put these, if you want to have an equilibrium, then this one, the velocities of these two must cancel. So they have to be rotating in opposite directions. Whereas if they're all positive, that's not possible. And in fact, the equilibria only occur when they're in a straight line. These two have to be opposite. And this can be the same, obviously. It can't be opposite to both of the opposites. So this one's positive, this one's negative, and this one's either positive or negative. No. That's how it works. And the strength is so that the velocities, the effect of these two, which are obviously opposite, one pulls it up and the other down, the velocities cancel. These ones cancel, and so they have to be in a straight line. It won't work otherwise. A little bit of geometry, and you can work out, given that the velocity is proportional to gamma over r, you can work out exactly what depending on gamma 1, gamma 2, gamma 3, what the distances between them have to be in order to get an equilibrium point. And it only works under this condition. Now, so equilibria, there are very few. So the other interesting basic thing I want to talk about are relative equilibria. So a relative equilibrium for a system with symmetry abbreviate it to RE. And RE is a solution of a symmetric dynamical system let's call it x of t, such that x of t is g of t, x of naught, where g of t is a one-parameter subgroup of G of the group. So that's the general definition of relative equilibrium. So in the plane, we have rotations and translations as our group. Rotations about any point and translations, uniform translations. So what one-parameter subgroups are there? Well, just that. Rotations about some point and translations. So we can start to analyze what, with the information we've got, what relative equilibria there might be. So, two vortices is nice and easy. Every motion is a relative equilibrium. So if gamma 1 and gamma 2 don't sum to 0, so gamma 1 is not equal to minus gamma 2, then there is a point. So remember, we have these conserved quantities. So in particular, I'm going to divide by gamma 1 plus gamma 2, which is non-zero. So that's some point. If gamma 1 and gamma 2 are, oh, I've drawn them with opposite signs. So here, let's say, well, it depends which is bigger. Depends which one's bigger. Let's call this C. The vortices so it's a little bit of elementary geometry calculation. Okay, so from the conserved quantities, we can show that at this point, however they move, this point given by this formula is fixed because it's a conserved quantity. I've just divided by gamma 1 plus gamma 2 for convenience. Well, more than convenience. And also one can prove that the distances of these two vortices from this point don't change. Just doing a bit of algebra with the conserved quantities there, using the modulus one, the third one. So one can prove that it rotates about the point C. So that's, if gamma 1 plus gamma 2 is non-zero, you always have that. While if so equal and opposite. So what directions do those two move in? Well, this is rotating this way, so this will move. If this is fixed, this will go in a circle around here. But of course, this isn't fixed. But instantaneously, it's moving that way at a certain speed, which is gamma 1 divided by the distance. And what about this one? The motion of this one is exactly the same. Because it's gamma 2, it's going up, gamma 2, but gamma 2 in magnitude is the same as gamma 1 divided by the distance. So they're going up at the same speed, and that continues. So they just translate together. So perpendicular to the line joining the two. So whenever gamma 1 and gamma 2 add to 0, then so that means we understand two-vortex motion just geometrically. You can just analyze that. It's easy to check what I've said there. Three vortices is more interesting. When was it? 19? Well, there have been quite a lot of people who have studied the three-vortex system over the 150 years since Helmholtz and Kirchhoff. Singh, the Irish mathematician, J.M. Singh wrote sort of most definitive work. So, but he didn't talk about relative equilibria, but he was certainly interested in them without having a general definition. Stationary motions, they used to call them. So there are some. So we've already seen when there are equilibria, special case. So if we take three vortices, something like that, no, it's not true. If the vortices lie at the vertices of an equilateral triangle. So it's like the three-body problem in celestial mechanics, the Lagrange solution. So it doesn't matter what strengths they are. They lie at the vertices of an equilateral triangle, then it's a relative equilibrium. So they will rotate. So it's a translation if, just like before, the total vorticity is 0, otherwise a rotation. There are also collinear relative equilibria. Sorry, I'll be with you in a second. I've lost it. All right. I want to talk about this. Reduction and stability and how that's relevant for these studying these vortices. So reduction in mechanical systems with symmetry has a long history, but in modern terms, it's a theorem of or in its general context, it's the theorem of Marsden and Weinstein, the same Alan Weinstein we talked about before, and also Ken Meyer, who had a similar theorem, not quite as clean as the Marsden-Weinstein theorem, but the idea is the same, and it was done at the same time. So it should really be called Mayer-Marsden-Weinstein theorem. So if we have, like here we had, I just looked it off. So suppose we have k conserved quantities. So this is a thing called the momentum map, and it has lots of geometry, which is important. And Rk So how do these arise? There's one of these for each sort of independent one-parameter subgroup of symmetries. Right? That's Noether's theorem. If you have a one-parameter subgroup or a one-dimensional generator of the Lie algebra of symmetries, then that you have a conserved quantity. So K would be the dimension of the group. Right? So, and in fact, it's a vector space, so it's actually, so to each velocity field or one-parameter subgroup, there is a function. So that means it's dual. So the right way to the abstract, the correct notation, or the correct interpretation of what Rk is the dual of the Lie algebra. So the G here is the Lie algebra, and this is the dual space. And in this example, it's important. So usually we don't worry about the difference between a vector space and its dual. But in some examples, it's important. And the actions of the symmetry group on this Rk, if we take some compose elements of the group, or well, no, let me. So the reduced space for a fixed constant, let's call it as it usually is, mu, in this vector space. So that means I'm fixing each of the constants of motion. So it's because the motion takes place with the momentum, or these conserved quantities are conserved, they're constant. So if we start at a point whose J value is mu, then after all time, the J value is also mu. So it takes place on these subsets, right? But these subsets have some symmetry. So the idea is to reduce by that symmetry. So this is the orbit space. So G mu is that part of the symmetry group that acts on this. And you can make it precise by understanding what the action is on the dual of the Lie algebra. So it turns out this is a symplectic. This is symplectic, and it's not always a manifold because you've done quotient by something, so you might get a singular space, but it's always symplectic in some sense, but it's a symplectic manifold in nice circumstances. A lot of what I'm interested in is what happens when it's not a manifold and it's a singular space. And what does that tell you about the bifurcations that can occur? So here, there's a difference between these two cases. So we've had two statements now, well, one for two vortices, one for three vortices, about the sum of the vorticities being 0, you get translations, and if it's not 0, you get rotations. So we can know exactly what these spaces are, what this subgroup is that we're going to quotient by. And if is non-zero, then G mu is SO2. So the picture that this is derived from is, I've rubbed out what J is. And so if I call this U psi, so psi is a real number, U is a complex number, then the points that G mu, if we act on M by a transformation, then we have to act on Rk by a transformation as well, and the orbits so this is what G star looks like. So it divides up into cylinders and points on the, so this is psi direction, points on the, those are points. So if the sum of gamma j is 0 and this is 0, then if you act by any element of the group, this doesn't change. This quantity doesn't change. It's a little lemma, you can prove it. Whereas lots of paraboloids. So it's there's this action of the group on this space, which produce these cylinders or paraboloids, and what you're interested in when you quotient here is the elements of the group which leave a point fixed. So if we choose some mu here, what elements leave that fixed? Well, it turns out in that case it's SO2. But in this case, if it's one of these points, then it's either the whole group or it's just if your mu is on one of the cylinders, it's a copy of the reals. So that's what you quotient by. But I'm going to look at this case first, only. Ah, yes. So we take, when we with some rotations, so vorticities in some orientations, like, I've forgotten now. The formulae here. So H is just written in terms of the r's. So this is what you can do after reduction. You get 4 pi h is minus gamma 1, gamma 2 log of R3 in cyclic permutations, and J, instead of being so we're in this setting, and what's left of J when we factor out the group is just which orbit we're on, and if we work it out, we get psi squared minus mod u squared. We get those. Now, what do we do with relative equilibria? It's where the Hamiltonian vector field is equal to the vector field for some element of the Lie algebra, because it corresponds to, the solution corresponds to a one-parameter subgroup, and that's the Lie algebra element that generates the one-parameter subgroup. So if we apply the symplectic form, we get so that's the Xi component of the momentum map. And this is the same as Xi dot dj. dh is Xi dot dj. So this is just a linear combination of, so j has got 3 factors, so it's just Xi1 times dj1 plus 1. So it's a Lagrange multiplier problem. So after reduction, we get dh, still given by the same expression, equals Lagrange multiplier. I'm going to use a different style j here. So still a Lagrange multiplier problem. I haven't got time, obviously, to derive it, but it comes from the same thing, but it's what you have when you've done reduction. And you find there are critical points of this. I mean, it's a very simple. You have now got 3 variables. Equilateral triangle. So that's how one does the calculation to prove what I stated before, that there are relative equilibria. I've lost it. No, must have been under here. So there are relative equilibria when for equilateral triangles, and then one can look at stability. So these in the reduced space, because so the original relative equilibrium is a motion which is along the group. So if I've factored out the group, we've removed the motion. So it's an equilibrium. So what I should have said, in the reduced equations, it's an equilibrium point, which happen when R1, R2, and R3 are equal, so equilateral triangle. So now we can apply the Lagrange-Dirichlet criterion, because we're just talking about equilibrium, whereas in fact, this is a periodic orbit, so the Lagrange-Dirichlet criterion doesn't say anything, but now it does. So we need to say D2H. So it's the usual way of looking at the Hessian after doing Lagrange multipliers. And it turns out that what one ends up with is 2 by 2 matrix, which is wonderfully symmetric between the different variables. So this is the quadratic form, and if you want stability, you want this quadratic form to be positive definite, so or negative definite. So work it out. I think it was greater than 0. Yep. So that's how we prove stability. So it depends on the circulations.
So that's formula gamma minus gamma 1, gamma 2, gamma 3 minus gamma 1, gamma 2, gamma 3 minus gamma 2, gamma 3, gamma 1.
This is R.
I mean,
Sorry, this is gamma and this is R.
R.
R2, R1. Yeah, sorry, I hadn't realized it's very similar. Yes. It's a function on, and this is R. It's a function that depends on the shape of the triangle.
Because gamma is a commutative.
Gamma is a real number. It just tells you how fast the vorticity is rotating, how fast the fluid is rotating.
So it's a kind of real thing about the direction of the rotation.
Yes.
So
Yes.
in the case of 1, 3 is not 3, 1.
They're just real numbers, so it doesn't matter which order. Yeah, 3, 1 is better. Yeah, here it's 3, 1. So we want to. So we know that this reduced thing, this reduced motion is stable. But do we know the original motion is stable? So this is an important question. Took quite a few years to understand. One can also ask questions about, we have an equilibrium with stable equilibrium, so we can look for periodic orbits like Lyapunov's theorem and so on. But anyway, let's just think about stability. So we have a point in our manifold, and this is all the points that you get by applying the group. And we have a trajectory that moves on the group. So that's what maybe it looks like irrational flow in a torus or something. That would be generically the case, but in SE2 it'll be simpler. It's either translations or it's rotations. So they either close up or they just go to infinity. Right? So here we have other group orbits, and these are all collapsed down. So each group orbit, so this is M, or the reduced space, part of M over G. So each point here corresponds to a whole orbit. So now we know by Dirichlet So we know that there are neighbourhoods such that this point here is, this equilibrium point is stable. Lyapunov's definition of stability. So what does that tell us about here? So the easy answer, there are two levels of answer. So the easy answer that's my question. I'll answer this and then I think I've finished. So so answer 1 G stability. So what do we mean by G stability? So, or G Lyapunov stability. The same as Lyapunov, but U and V are not any neighbourhoods, they're invariant neighbourhoods. So it's a neighbourhood that contains the whole orbit, all the points that are similar in. So if you have if your particular solution is a translation, then your open set would be containing all possible translation. So it's a huge set, but that's what this theorem tells you without any further thinking. So it's Lyapunov stability. So this tells us that if we take a point, M, which is a relative equilibrium, which is stable down here, and we take any little deformation of it, okay, so the idea of stability is if you deform it, you don't move far away. But what this is saying is we don't move far away from this orbit. But we could move a long way, particularly if the orbit is not compact like it isn't for a point vortex system. We could drift a long way away. So, but one can do better. And that's a nice theorem of George Patrick. So if G mu is a compact group, so have I still got that written down? Yeah. So if gamma 1 plus gamma 2 plus gamma 3 is not 0, then G mu is just the rotation group SO2, so it's compact. Then you don't just get G stability, you get G mu stability. So this means so that you couldn't expect better. You've probably heard about orbital stability. So if you have a periodic orbit, in what sense would it be stable? It's certainly not true that if you start nearby, you stay nearby this point. But what you expect is you stay, or what you hope is you stay nearby this periodic orbit. Right? And that's precisely what you're getting here. It's G mu stability. G mu is SO2, which is a circle. And the trajectory would be, when this sum is not 0, the trajectory is, I haven't written it down, is rotations, like it was for two vortices. Did write it somewhere. So that's compact. So So the relative equilibrium will be periodic because it's just rotation about some point. And this picture is as good as you would hope to get. This does not work when gamma 1 plus gamma 2 plus gamma 3 is 0, because then G mu is not compact. So the best you can do then is just the easy answer, which is G stability. Okay, any questions? Thank you for lasting so long. Yeah, okay. Should we call it a day? No, that's fine.
Thank you very much.
Okay, pleasure.